In this video I'm going to try to do an overview of the subject of physics and chemistry of 2nd of SO years 2017-2018. So I've prepared a brief index which includes the contents that we are going to see, which there are probably most of them, and we have things from scientific methods, lab equipment, physical quantities, changes, atoms, and physics in the end. So, the scientific method. What's the scientific method? It's a set of ordered steps. They have some... it's composed of some steps, which they are ordered, and they are used mainly to find new knowledge in science. The steps are the following. First, you have to identify the problem. This means that, for example, if you've seen something that you'd like to say, why does this happen? Then you have to research the problem, check in the internet or in some books of science. If someone has already done work about that, maybe to help you out with your investigation. Then you have to make a hypothesis. A hypothesis is what you think is going to happen. Then you have to test the hypothesis with an experiment using a fair test with repetitions. We're going to have a look at the first test now. When then you're going to arrive at a conclusion after several repetitions, and in the end you have to report the results of your experiment. So a fair test has only one independent variable and one dependent variables. All of the other variables, they have to be controlled. That's why they're called control variables. So this means that one independent variable is going to give the value to the dependent variable. This is like in maths, like a function. You have the independent variable, which maybe it's x, and then you have y, or function of x, that it's going to be the result. So how to report the results? When you finish the experiment, you have to report the results, rating, and a specific work. You have to first include the title, then an abstract, which is going to be like a short summary, an introduction, where you're going to explain the purpose of the experiment, etc. Methods and materials, for example, if you use maybe lab equipment, chemical compound, etc. Then you have to include your results. After the experiment, what has been the result. Then a discussion where you're going to explain how you arrived to those conclusions, indicating the steps you followed, etc. Then conclusion with clear statements. They must be very clear statements, so another person could repeat the experiments and have the same ones. And finally, you have to include references and bibliography that you used to perform that work. Then, variables in experiments. We've mentioned the three most important ones, which were the independent variable, the dependent variable, and the control variables. An independent variable is chosen by you, and you have to give it values. The dependent variable gets their value from the independent one. That's why the dependent one depends on the independent one, because it doesn't depend on anything. And finally, we've got control variables, which are all of the variables that can make a difference in the value of the dependent one. Maybe temperature or pressure, for example. And we have two types of variables. They can be quantitative or qualitative. Quantitative means that you can assign it a numeric value, where the qualitative, you cannot assign them a numeric value, like for example, the color of your hair. Graphs are visual representations of relations between variables. We mainly use three types of them. Graphics are great when you want to explain things in a very, very visual way, because probably most of the people would understand it. Bar graphs are going to be the first ones, which they are composed, like you can see, of bars labeled, and the x and y axis, they're labeled properly. The bars have the same base. They're a rectangle and they have the same base, and their height is the dependent variable. For example, here in rabbit, the dependent variable would be 4, and that's where the line gets to, or the height gets to. Then we have the pie charts, which they're on a complete circle of 360 degrees or 2 pi radians, and each sector is labeled with a color, a percentage, or even the text. Here we've got this legend here and some colors, and they show us the percentage for a clear view. Finally, we are going to see the ones which are used in science, which are called scientific or line graphs. This means that you represent all of your results with some dots on the x and y axis, and then you have to draw a line which fits the best for each dot, that means that the line should be the closest as possible to each point. So using this line, we would be able to approximately get the results of another test. Physical quantities. Physical quantities are characteristics of an object or event, measured or stated by number. That's very important. They have to be quantitative, not qualitative. For example, maybe length or pressure. And we can distinguish two types. The first one, which are fundamental, that they are not the base, they are not the product from the combination of other quantities. And we have 7 base quantities, or fundamental. And then we have the derived quantity, which comes from the combination of 2 or more fundamental quantities. In this table, we can see the 7 base quantities and the units in the SI system. So the SI system was introduced in around 1960s, and they established 7 base units and their symbols. So length, mass, time, temperature, amount of substance, electrical current, and light intensity. Length is measured in meters with a symbol m. When this means the kilograms, the symbol is kg. Time is measured in seconds, and its symbol is s. But sometimes the abbreviation SEC is used. Temperature is measured in Kelvin, not Kelvin degree, and its symbol is a capital K. The amount of substance is measured in moles, and the symbol is mol. The electric current is measured in amperes, and its unit and symbol is A. And finally, the light intensity, which is measured in candelas and has a symbol CD. When you are performing, when you are writing a report, maybe of an experiment you've done, you should always give the units an SI value. Well, the units should be SI always. And each unit has also submultiples and multiples. When, for example, a unit is too big or too small to measure a quantity, we use these ones. For example, if you want to measure the length of a paper, you won't use meters because that's maybe too big, but you can use centimeters or millimeters in order to get a clear result. These are the SI prefixes, which these ones here on the left, they are for greater than the base units, and this one, they're smaller than the ones on the base units. So they're deca, hecto, kilo, mega, giga, tera, peta, y hexa. And the these are called multiples, and these are the submultiples. Deci, centimilo, micro, nano, pico, femto, y ato. And they have their own letter. For example, the example of the paper. Maybe meters, it's way too big for these small measurements. And the conversion of units. I'm going to introduce you a very simple rule, but it's going to be very effective when we see it in a practical way. which is what is above goes below, and what is below goes above. To convert units, we use the conversion factors. And this is going to enable us to cross out both units and leave us with the units that we want. So maybe that's quite confusing, but here are the steps, and I'm going to explain it with an example. First, you have to establish the relation between the units you want to convert. For example, imagine that you want to convert 1 kilometer to kilometers to meters. So you have to establish that 1 kilometer equals 1,000 meters. Then, using this rule that we have here, we can prove that 1,000 meters divided by 1 kilometer, which is the same, it's going to leave us 1. And a number times 1 equals that number, so nothing is going to change. Then we have to write the complete equation by multiplying the proportions. These proportions that we have here. For example, transform 3 kilometers hour into meters per second. So we have this equation. 3 kilometers divided by 1 hour, it's going to be 3 kilometers divided by 1 hour times 1,000 meters divided by 1 kilometer times 1 hour divided by 300 seconds. As you can see here, this kilometer with this kilometer, it's going to go, and this hour here with this hour here, it's going to go, leaving us with meters and seconds. So remember the rule here. What is above here, the kilometers, they have to be written below. And what is above, what is below, the hours in this case, they have to go above. Once you have them written, you have to establish the proportions, which are 1 kilometer equals 1,000 meters, so you write it then. And 1 hour equals 3,600 seconds, and you write it there. And you just simply operate this, and that would leave you with the final result. So as you can see, the units have been cancelled, and the result is in meters per second. Now we're going to talk about changes, physical and chemical ones. A physical change is a change in a physical property, like for example, shape, color, and there is no change in the molecular structure of substance, and it's observed with senses. Chemical changes, there is a change in the molecular structure of the substance you have. It indicates how a substance reacts with another one. So these changes will make matter change into another one, and they are mostly irreversible. It's very, very complex to undo a chemical change, whereas the physical changes can be simply reverted with physical means. Lab equipment, it's necessary to know the names of the equipment that are used in a laboratory. If you want to carry on an experiment and you're, for example, with a friend and you have to use something but you don't know its name. So this is a picture with the most common elements and material used in a lab, which they go from Bunsen burners to heat up mixtures. You have Erlenmeyer flask and beakers, Erlenmeyer flasks to maybe to mix substances without spoiling them, a beaker, wash bottles to wash my equipment. You have graduated cylinder to measure quantities, and thermometers to measure temperature, etc. So Haskam symbols, they're very, very important when we are handling dangerous chemicals, and dangerous chemicals are going to have them always. So they are diagrams that indicate some of the common hazardous chemicals used in chemistry. Maybe that sounds weird, and hazardous, it's peligrosos, and it looks like a tongue twist, but not. Physical hazards are explosive. Well, the most common ones are explosive, flammable, oxidizing gases, well, compressed gas, and corrosive to metals. Whereas health hazards indicate toxicity, skin corrosion, skin irritation, or maybe aspiration, heart problems, etc. We also have environmental hazards, which they can cause very, very bad effects on the environment, which it's this kind of one, which it's very easy to recognize. It was like a dead tree and a fish out of the water. Elements, compounds, and mixtures. An element is a simple substance made up of one type of atom. and it cannot be split into something simpler by chemical means. In the periodic table, we can see all of the elements, there are 118 ones, and they are all different from each other. Elements can be mainly metals and non-metals, but they can also be noble gases, semi-metals, etc. The main characteristics of metals are the following ones. They are great conductors of electricity and heat, they're shiny, solids with very high melting points except for mercury, which at the room temperature it's liquid. They are located in the left side of the periodic table, and 3 of them are magnetic. They burn to form alkaline oxides and they are flexible. A great example for this is copper, which is very flexible. Then we have the characteristics of non-metals, which are their poor conductors, dull, solid, and gases. They're located in the right side of the periodic table. None of them are magnetic, and they burn to form acidic oxides. They're also brittle, which means fragile. When atoms join together, they form a compound. If the atoms are different, we have the compounds. If the atoms are the same, we still have an element. For example, with oxygen, we are never going to find oxygen just like a single atom, but we'll find a molecule which is going to still be an element. And compounds usually finish in -id. For example, carbon dioxide, CO2 finish in -ide. Mixtures. Mixtures are the result of the combination of compounds and elements, and there are no reactions between them. They can be easily reverted or separated by physical means. Mixtures are made up of 2 or more compounds which are not chemically bonded. That's very important, and they can be separated easily by physical means. Solutions are a kind of mixtures, but they have some differences. Some solids are soluble, for example, in water, and a solution is made of a solute and the solvent. The solute is what we are going to try to dissolve, and the solvent is the liquid where we are going to dissolve the solute. A solution is always clear. That's very important. So we can establish this simple equation that would be solute plus solvent equals a dissolution, or produces a dissolution. The total mass of a solution is the sum of the weights or the mass of the solute and the weight of the solvent. Solids which don't dissolve into a specific solute, they're called insoluble in something. For example, cinnamon, which is canela, is insoluble in water because they cannot be mixed together. Some solids may not dissolve in water, but they might also dissolve into another ones. For example, in ethanol. The concentration of solutions, it's how much solute is dissolved into a certain amount of solvent. The formula is mass of the solute measured in grams divided by the total volume measured in liters. So this leaves us with a concentration of grams per liter. Solubility is the concentration of a saturated substance. We can distinguish 3 types of solution. When the concentration is far less than the solubility, we'll be having a diluted solution. When the concentration is similar to the solubility, it's called concentrated, and it's saturated if the concentration is equal or greater than the solubility. This would make the solute precipitate. So we would be able to see like some solute on the top in the bottom of the beaker or the object we're using for holding these substances. We can distinguish 3 states of matter, which are solid, liquids, and gas. Solids are made up of particles which are very, very close together, and they create strong bonds. That's why they're usually very hard to break, and they cannot be squashed and don't flow. They don't flow. They have fixed shape, and a fixed volume. That means that the shape is not going to change unless it's broken, and the volume is going to still the same, and they have a high density. On the other hand, liquids are made up of particles which are quite together, but the bonds are weaker than in solids. Liquids cannot be squashed and they flow easily. They have a fixed volume but not a fixed shape. That means that they're going to get the shape from the container they are in, and they usually have lower density than solids. And finally, we've got gases, which particles are well spread together without bonds. They are easy to squash and they flow easily, and they don't have a fixed shape or volume. They're going to occupy as much space as they have, and they have lower density than liquids. And the change of state. A change of state is, the state is a physical property, and they can be changed by adding or removing temperature. So, as you can see here, this would be, for example, water, and this shows us the relation and the name of the name of the change of state. For example, when it's in a solid and transforms into a gas, that's called sublimation. When it's solid and it transforms to liquid, that's called melting, and when it's gas and, for example, it turns into a liquid, we would have a condensation. This is called the heating curve, which is more visual on the temperature. Well, gives us a better representation of the change of state in relation with the heat added. When, as you can see here in this graph, when heat is added, we would be having a change of state. Also, we can distinguish another thing which is called molarity. Molarity is the number of moles present in an amount of solvent. This is a way to measure the concentration of solutions. So we can, the equation is molarity equals the number of moles, which we're going to call it them M, measured in moles, and the volume, that we are going to call it V, and it's going to be measured in liters. So following this property, we can establish that the number of moles is the molarity divided by the volume, and the volume the molarity times the moles. For example, a way to calculate molarity would be, the best way to see this, it's going to be an example. So calculate the molarity of sulfuric acid in a total dissolution of 1 liter of water. So the first step is to calculate the molar mass of the sulfuric acid. So we can have a look in the periodic table, and we'd see that the molar mass of one atom of hydrogen is 1, of sulfur it's 32, and oxygen is 16. These are measured in UMA, which is unidad de masa atómica. So we'll be having the molar mass, it's going to be the sum of them. So we have 2 atoms of hydrogen, so 2 times 1 plus 1 of sulfur, which is 32, plus 4, as you can see, there's 4 atoms of oxygen, times 16, which is approximately 98 grams per mole. So we can use some proportions to see the amount of, that's going to be this 98 means that in 1 mole of sulfuric acid weighs 98 grams. So we can use proportions to identify, to know how much does 12 grams of this weight. So that would be 12 divided by 98 moles, and it's 12 per 0.12 grams. So given this, we can calculate molarity is the number of moles divided by the volume of the solution. So it would be 0.12 moles divided by 1 liter. That would mean that molarity is 0.12 grams per liter, not mole. I'm confused here, sorry about that. Atoms. All matter is made up of atoms. Atoms consist of electrons surrounding a nucleus that contains protons and electrons. So, a person who advanced the science related with atoms was Dalton's, and he wrote his theory, which is called Dalton's theory of matter, which is the following. All atoms are made up of all matter is made up of atoms which are indivisible. All atoms of a given element are identical in mass and properties. Compounds are the combination of two or more different types of atoms, and chemicals are arranged in a chemical reaction. So, an atom has this shape, which is divided into the nucleus and the outer layers. The nucleus contains protons and neutrons, and the outer layers contain the electrons, which are flowing between these orbits. The proton has a positive charge, a mass of 1, and it's expressed with the letter Z. Neutrons have they don't have charge. They're neutral. We could say that they're neutral. That's why they're called neutron. And they have a mass of 1. They just support the mass, and they're expressed with the letter N. And electrons, they have a negative charge and not mass. Well, it's very, very few, so we say that it hasn't got mass, and it's expressed with the letter E. So, when atoms come together, they can form bonds. The two ones that we've studied this course are ionic and covalent. There are the difference between them. Ionics are metal-metal or non-metal with a metal, and covalent bonds are made between two non-metals. They are mostly opposites. For example, in ionic there is a total transfer of electrons, whereas in covalent they share atoms. In ionic bonds we have a high melting point and boiling points, whereas in the covalent points we would be having very low boiling points and melting points. An ion. An ion is an atom that has a non-zero electrical charge. So this means that the number of electrons is not equal to the number of protons. For example, given oxygen, which has 8 protons, for it to not be an ion would be they had to have 16 electrons. So, for example, if oxygen plus, that they're expressed with a plus, the mass would be with the number of protons would be 8, but they would be having one less atom, so that would be 7 and not 9. I've confused them now, I'm sorry. Chemical reactions and the oxidation of metals. When two elements are joined to cause a chemical action, no matter is made or lost. We use balanced equations to show what happens to atoms in reactions. So, given, for example, the oxidation of copper, the word equation would be like talking copper reacts with oxygen to produce copper oxide. If we were just having atoms, it would be copper plus O2 would be copper oxide. But as that's not possible, we have to use a balanced equation, which means that two atoms of copper join with the two atoms of the molecule of oxygen. Copper can make 2 bonds, and oxygen has 2 bonds left, so they just combine perfectly. Another way to see this, it's in a graphical way. 2 atoms of copper, which are separate, they react with a molecule of copper, creating us 2 molecules of copper oxide. So, in a diagram, forces are pushes and pulls. They can change the speed, size, shape, and direction of an object, and their SI unit is Newton, which is kilograms times meter divided by second square. So, for example, given this airplane and this diagram of forces, we can distinguish some vectors, which they are they meet together at that white circle, which we're going to consider that as the origin. So we can say that measuring them, the vector from OA, it's 12 millimeters, OB 7, OC 8, and OD 5. So if we're given that 1 millimeter equals 1 Newton, we can find see the final movement on the x and the y axis. So how do we do that? The movement on x, I'm going to call it r over x. It's minus 12 newtons, because if we in the Cartesian plan, a would be negative on x, plus the 7 of OB, which in the Cartesian plan they would be positive. It's minus 5 newtons on the x component. And on the y-axis would be the same. We have 8 newtons pushing up and 5 newtons pushing down. So we have to subtract them, because d in the Cartesian plan on the y-axis would be negative. So that would be leaving us 3 newtons, and we can graph this final vector on the in the Cartesian plan, as we have the component x, which is going to be 5, and the component y, which is 3. So the airplane would be traveling kind of like this. So Newton's, which is this person here, wrote the laws of motion, which they are the following. A body at rest will remain at rest unless it's acted upon by an external force. This means that an object is going to stay at rest unless we push or pull it, for example. The force equals the mass times acceleration. And finally, for every action there is an equal and opposite reaction. That's called the normal force. Or on springs, working with springs, we use the Hooke's law, which means it states that in a spring the extension is directly proportional to the stretching force. So force is equal to the spring constant times the extension, which is mathematically expressed like this. And the force is measured in newtons, extension in SI units with meters, and the spring constant is measured in newtons times meter. That's why we multiply the extension times the newtons divided by meter, leaving us newtons, which would be the force. So for example, using Hooke's law, let's solve out this problem. If a spring is 35 centimeters long and we apply a force of 2 newtons, it stretches to 0.38 meters. What would be the spring constant? So using the Hooke's law, it would be extension equals the force divided by the constant would be the force divided by the extension. So the extension would be the final length minus the initial length. So it would be 3 centimeters and 0.03 meters. So we have to always to work in SI units. So as force equals the constant times the extension, the constant will be the force divided by the extension. So the constant will be 2 newtons divided by 0.003. Oh, that's 0.03 meters, and would leave us 66.6 newtons per meter. So force and acceleration. A force would make an object accelerate. Force is mass times acceleration, as what states the second law of Newton. For example, we can have weight, which is a force measured in newtons, in different planets. For example, I've built this table, and if our mass was 50 kilos in our mass, and on each planet we would be having a different weight, because that depends on the acceleration due to gravity. On Mercury, it's 3.6 meters per second square, etc. So this would be the result, our weights in our different planets, just as a curiosity. And the Archimedes principle. It states the following. any body completely or partially submerged in water, in a fluid, it might be a liquid or a gas, at rest is acted upon by an upward or buoyant force of the magnitude of which is equal to the weight of the fluid displaced, which is called upthrust by the body. So we can establish a relation which is weight equals upthrust. We're going to have a look at this later. So the upthrust, it's going to be this. If, for example, we have this this recipient with water, and we add a mass of 5 kilos, the level it's going to raise up 5 kilos. So, for example, we can see clear with this example. When the 2 kilograms are submerged in the water, it's going to expel the same amount as the weight which was inside. So, an example. I took this problem from this side here, and it says the following. You plunge a basketball beneath the surface of a swimming pool until the half of the volume is submerged. If the basketball radius is 12 centimeters, what will be the buoyancy force on the ball due to water? So, buoyancy force, it's going to be following the Archimedes principle, the upthrust. So, matter displaced will be the density of the water times the volume displaced. So we're going to first start calculating the water displaced, which is going to be half of the volume of the basketball. So given a sphere, volume 4/3 of pi times the cubic radius, we just multiply them and we get 2/3 of pi times the cubic radius. We pass the radius to SI units and we solve this equation. Buoyant force would be the same as the water displaced times the matter displaced times the gravity. So equal to the density of water times the volume displaced times the gravity. So given density of water approximately 100 kilograms per cubic meter, we multiplied by the volume of the sphere which was inside and multiplied by the acceleration due to gravity, and this would leave us with the weight the buoyant force which is acting on the water, which would be 35 newtons. In a distance time graph, the average speed is the slope or the gradient of the graph. The steeper the gradients, the higher the average speed. An horizontal line, which means that the gradient equals 0, means that it's stationary. For example, this graph here. Moving, the fastest one would be the segment A, because its gradient is the biggest one. It's stationary on line C because its gradient is 0. It's returning because the D because its gradient is less than 0, and the average speed would be in this point, would be in the first one the division of the distance. In the speed time, we have it has some properties. If the gradient equals 0, we have a constant velocity. If the speed is equals to 0, it's stopped. And if the gradient is bigger than 0 and it's a straight line, it would be speeding up. Whereas if the gradient is less than 0, will be a straight line going down, which means that it's going to slow down. For example, in this graph here, the acceleration would be m, the gradient of each line. So the acceleration on the line on the left would be, using the formula, acceleration equals final velocity minus initial velocity divided by time, would be having 10 meters per second minus 0 meters per second divided by 2 seconds. That's what the time it has taken for it to reach that velocity. So we could be saying that we be having an acceleration of 5 meters per second square. And the distance traveled is the area under the line. For example, on the first red line until the constant speed would be a triangle, which would be base times height divided by 2. So we're having 4 seconds divided by 8 meters per second square divided by 2. So that would leave us 16 meters. So that's what we've traveled. Movement. A movement is a turning effect of a force. Force can make object turn if there is a pivot. So movement is measured in Newton's meter, which is force times distance, which mathematically can be expressed as m equals fg. So if the system of forces is balanced, we'll be having that force 1 times the first distance will be the second force times the second distance. So, for example, if we have this seesaw, 10 newtons going down at a distance of 2 meters from the pivot would keep the seesaw, which is balancing, balanced if there is the distance from the pivot is 1 meter and the force on the right hand it's 20 newtons. So we are having the same movement on both of them, so they will be balanced. And we're going to be ending up with, well, not finally, but we're going to see mechanical energy, which is the kinetic energy plus the potential energy. The kinetic energy of an object expressed as ek or E sub k, it's the energy an object has because of its movement, and it depends on the mass and the speed of the object. And its formula is 1/2 of the mass times the squared velocity, and it's measured in joules. The SI unit is joules. And we can also establish that the velocity would be the square root of 2 times the kinetic energy divided by the mass. And the gravitational point, it's called GPE, it's the weight times height. So on the Earth's surface it would be mass times gravity times height, where G would approximately equals 10 meters divided by second square. Sorry. So we can calculate the kinetic energy of a 60 kilograms athlete running at 10 meters per second. So it would be 1/2 times 60 kilograms times 10 meters per second square. So that would leave us 300 joules. Mechanical waves. A wave is the propagation of a disturbance generated at a point in space which transports energy but not matter, and it has some properties. Amplitude, which is a capital A, it's the maximum distance between two points oscillating relative to the equilibrium, and it's measured in meters. The wavelength, which its symbol is lambda, this Greek letter, it's the distance between two crests or two troughs, and the SI unit is meter. We're going to see in a picture all the parts of the wave so you can understand it better. Period, which is T, is the time it takes a wave to travel its own wavelength, and the SI unit is seconds. Finally, frequencies. The frequency is the number of wavelengths traveled in 1 second, and it's the inverse of the periods. SI units, it's hertz, which is capital H set. And this is very important. The greater the amplitude or frequency, the more energy it carries. So this would be the example of a wave. The red one will represent the amplitude, which is this segment here. The wavelength, as we said before, it's the distance between two crests or two throats, and the direction of the wavelength is given by the position on the x-axis. Sound is a propagation of vibrating objects throughout a medium, and they're also waves. So they have an intensity, which is the energy in the sound wave, and that's what we call volume every day, and it's measured in decibels, which is dB. Pitch is the frequency of a sound wave. The human ear can perceive frequencies between 20 Hz and 20,000 Hz. Then we have the timbre, which if two instruments play the same note or pitch at the same intensity, we may distinguish them. That's why, for example, if we play a guitar, in a guitar the same note and in a flute the same note, we're going to be able to distinguish them, or maybe two voices. Noise pollution, which is another characteristic, refers to the excess of annoying sound, which is called noise, caused by human activities. And finally, thermal energy and heat. Thermal energy refers to energy possessed by matter due to the movement or due to the disorderly agitation of the particles that made it up. Temperature is the physical quantity that indicates the thermal agitation of the atoms or molecules composing an object or a material system. Heat is the flow of thermal energy between two bodies at different temperatures. And thermal equilibrium, we say that two bodies, A and B, are in thermal equilibrium if they have the same temperature. Heat propagation. Heat can spread in three ways, which are conduction. Heat propagates throughout